My name is Hong Ma. I'm a professor in the Department of Mechanical Engineering and also a faculty in the Center for Blood Research. So for the first afternoon session, we have first two trainee talks. So the first trainee is Emel Islamzada, who is actually my PhD student, and she did a wonderful PhD, and this is the very last part of it, which has just recently been accepted for publication. So come on up, Emel. Oh, okay.
All right, pardon for that. Hi, everyone. And first of all, thank you guys so much for giving me the opportunity to give this talk. And this is the work I'm very excited to present. And hopefully, I won't just give you a snapshot of what we've done for this particular study, but also a bit of a story about how we actually got here and where we're going from here, because this is a part of a larger study that's going really well. And we're extremely happy to share it. So I think in this crowd, all of us are well aware that deformability is quite important for red blood cell function, and red blood cells are the ballerinas of the cell world. They have to deform over and over each hour, each day in order to perform their function. We also know, and this has been discussed before, that a good healthy donor is different from a good healthy donor, is different from a good healthy donor. So my red cell unit won't store the same as your red cell unit. So when we come up here, and we end up with a very heterogeneous pool of red blood cells, what does it mean for different patient populations? When we talk about chronic transfusion patients in particular, and those are the ones that have repeat transfusions, perhaps even lifelong transfusions, how do we ensure that we give them the longer circulating units? And since we know that deformability is important for red blood cell function, can it potentially perform as a biophysical marker for the circulation time? Now, there is a plethora of methods to measure red blood cell deformability. I won't go into too much detail, but there are methods that will give you an average deformability score. There are methods that will look in a small fraction of cells and give a lot of information about deformability of each one of them. What Kwan Kuo in our lab did is he made a device that acts a bit more like a spleen on chip. So what it does, it sorts red blood cells based on their deformability into distinct different fractions. So you can study each fraction on its own. You can study them all together. You get different populations of cells, and black and red and green are separate cell samples. And they have different deformability curves. So black and red are quite similar, and they're relatively more deformable than a sample represented here on green. So once we had this new method to evaluate red blood cell deformability, we had a few questions. First question was, well, if we look at a pool of healthy donors, can we actually tell the difference between them by looking at their deformability on day one? And the answer to that was yes, donors are actually quite different in their deformability signature. Our next question was, well, so what? If I donate now, and then donate 2 months from now, and then donate a year from now, will my deformability signature be the same? And from what we've seen so far, the answer to that is yes. If we come and donate weeks apart, from what we measure with microfluidic ratchet device, our deformability profile will stay consistent. And next question after that was, what about the stored blood? What about the stored units? And we did show that there is a progressive loss of red blood cell deformability in these stored units, and we have these works published in the papers here for more information. But again, the question is, so what? So deformability changes, it gets reduced, but can it potentially be predictive of a circulation time after the unit is transfused? And to answer this question, is red blood cell clearance deformability dependent? We went to a mouse model. So we had two potential models. Model one is red blood cells are cleared regardless of deformability. There are other more important players involved. Or there is a particular point of rigidity at which you shall not pass, and you'll be cleared away. To answer this question, we designed a fairly straightforward study, at least straightforward on paper. We took donor BL6 mice blood, divided them into control and AMT treated. So aminotriazole is a mild oxidating agent. It won't kill the cells. It will make them a bit more rigid, though. We confirmed the deformability shift between control and AMT treated cells. We stained them, transfused into the same recipient mouse, and checked the deformability over time of all three cell populations: control, rigid, and endogenous. So what we found was quite interesting. So let's focus on the top panel right now. So the solid colored lines are the deformability curve before transfusion. Dashed line is the deformability curve after transfusion. And the black line is the endogenous deformability of the recipient mice. If we look at control, the deformability of cells before and after is very similar and closely related to those of endogenous cells. It's interesting to see that prior to transfusion, this was a curve for the AMT-treated small rigid cells. Dashed line is the curve after. So the curve closely matches the curve of endogenous cells, and there's a bunch of cells that are rigid that have been cleared, which is also quantified over here. So roughly 25% of the most rigid cells were cleared away. And after this initial clearance happens, interestingly, if you look at this graph, so for control, the clearance rate over a period of 5 weeks that we tracked is about 21 days, and it's very similar to AMT-treated cells as well. So whatever clearance happens, it happens in the first 24 hours. And once the deformability curve matches the endogenous cells, these cells just keep circulating pretty much as normal. So I hope I've shown you that we have support for our model 2, that there is a you shall not pass rigidity score beyond which cells do not persist in circulation, at least from N of 7 mice that we had a look at so far. And the deformability of transfused red blood cells in circulation matches the deformability of endogenous cell population. This is all poster 5. I also want to pitch our poster 6, which is presented by Eric in the back here. Our next step was to do a non-interventional clinical study where we have a cohort of stable thalassaemic patients. They get regular transfusions. We get segments from these transfusions. We look at their deformability and compare it to hemoglobin increment to see whether there is a different, better or worse or no difference of hemoglobin increment depending on what deformability the unit had at the time of transfusion. And you can talk to Eric at poster 6 for that data. Thanks a lot. Thanks for the opportunity to give this talk. And ask away any questions.
Thank you, Emel. So, any questions?
Hi, Emel. Thank you so much. That was really wonderful. I just have a question. It came up earlier this morning about the switch away from the plasticizer DHP in the red blood bags. Can you speculate on how you think that might impact what you've shown in your research, and also, I guess, clarify if most of this research was done in red cells in like regular blood bags with DHP?
Yeah, that is very interesting. So we do see a rigidification of cells over time in DHP containing cell units. So that's going to be different once we change the bags as well as storage solution. It depends on how well the storage solution will kind of compensate because I assume the storage solution will still aim to keep the cells at their best. Deformability, and there are certain factors also after transfusion that cells will be able to replenish, like ATP, for example. So the changes that happened aren't necessarily irreversible. So that will be interesting. It's hard to predict. Definitely the profile that we see here would have been different, but it doesn't necessarily mean that it will be detrimental.
I have 2 questions. Do you know if the lipid bilayer composition changes? Here, sorry, yes. I should get up. Sorry. So if during cold storage the lipid composition, membrane composition changes, this is one question what I have, if you know that. Secondly, is do you know where and how these cells are removed?
Oh, two excellent questions. Thank you. So we haven't looked at the lipid bilayer ourselves, but we know from previous studies that yes, there is a cumulative change that happens. And that change seems to accelerate near the end of the storage life. So it's going to be more on week 4, week 5, week 6 versus in the very beginning of storage. We haven't looked at it separately, but we do think that it will be one of the host of things that affects the overall red blood cell deformability. We'll look at it as a sum of all the changes that happen, not each particular one, although that will be a very important one. And when it comes to where the cells are retained, that's also an excellent question. So one way to answer that would be to have extra mice that we transfused, and after transfusion, say half an hour, 1 hour, sacrifice them and have a look at their spleen and liver. We haven't done that, but thanks for bringing it out. That will be a very interesting study to do on its own as well.
Thank you. A follow-up question quickly to do you know if the lipid composition of red blood cells differs between donors?
Excellent question. I am not sure. That's not something that we looked at, but that's an excellent question as well, because that will affect the deformability as well.
Yeah, great talk.
Hi.
Nice work.
Thank you.
I'm just it's a comment, I guess. I found it interesting that you lost about 25% of the cells, I think, in the animal model. Is that right? So I'm just thinking back to when people used to do chromium survival studies, and the FDA, or maybe it was the AABB and the FDA, but they said as long as you have 75% survival after 24 hours, it's a good transfusion.
Yep.
So I'm just wondering how much of that might have been due to deformability.
Yeah, that's an excellent question. So when we do a model of storage of marine cells, we don't actually see a big reduction in deformability, which is interesting. We did see it with a mild oxidizing agent, so aminotrazole is a catalase inhibitor, so it will slowly increase the amount of oxidative stress in the cell that will lead it to be removed. And of course, it is a question of is it deformability on its own, or if it's other things that are involved as well. From what we saw, the cells that were made more rigid, we did a whole panel of different concentrations of drugs. So we used the smallest concentrations that made them rigid, which was quite small. Looking at the literature, so I do believe it's heavily dependent on deformability. That being said, it will be really useful to do a panel of different markers and see what else is changing that can be contributing to removal. That's absolutely still out there. Thanks, Don.
Excellent.
Okay, awesome.